All right, it seems so. All right, so it's a pleasure to welcome Mark Crowley here today. Mark did his PhD in the Department of Computer Science here. And after that, he went to Tom Hicks' lab in the University of Oregon State University. He was there for a couple of years, and for the last 5 years, he's been at the University of Waterloo in the ECE department. Has been doing spearheading lots of AI work there. And when last year we had a symposium on forest fires, with Mark who was invited here as one of the main keynote speakers. So it's a pleasure to welcome Mark. Thank you.
Thanks for having me. Everybody can hear me all right? Let's get this microphone, so it's good. I'll just hide behind this thing. Yeah, so it's great to be here. And I'm, like you said, I have that on my own slide for the first one. Let me just figure out now a better way to see my own slides. Yeah, so that fire session last year was really interesting. And I'll get talking a little bit about some of the reasons why I would be at a fire conference as I'm a computer scientist. It's really interesting to be giving this talk here in the ECE department because I was from CS, so I've never crossed that bridge unless I'm just trying to get this, Starbucks or whatever without going outside further. But now I'm in an ECE department, so it's like it feels right. Well, welcome. And what else did I do here? So I'm also doing like a faculty research fellow at Element AI, and at this we have our own institute. So this is the CAIDA talk. So we have the Waterloo.ai institute because everyone has to have an institute. That's how it works. And we have seminars there as well. So it's nice to have a good way to connect everyone on campus, figure out who's doing AI and who's even using it in some way. So the same kind of things there. A lot of just talk about that a little bit there. And the focus with the Waterloo one, I know yours seems to be focused on like decision making and actions, which is awesome because that's like what I want to do, and I think it's very important. The one at Waterloo, because we have so much industry connections and co-ops and all this kind of stuff, right? They have this connection between like fundamental and operational AI, so the kind of engineering and the math dichotomy of all these things, how to make it and how to apply it, right? So since we're a very engineering heavy university, there's a lot of these stuff for healthcare, medical imaging, autonomous driving, that kind of stuff. But it connects people from all across the campus. And yeah, so they've got their own figures that, they want compact, transparent, open, AI things, but always focus towards, not necessarily just deployment and applications, but operational, so like reasonable, use cases and, lots of focus on how to have confidence in the models and interpretability. But it's really coming together very multidisciplinary, which is very exciting. So what I'm going to talk about today is a bit of just some motivation of my own kind of research, how it grew out of what I was doing here, but David didn't say I did a PhD with him, so kind of connected out of research from his group. And then talk about a couple kind of main topics kind of in my research lab and kind of talk about recent results and future things we're planning to do, just to kind of grab bag a few different topics that are kind of top of mind with me right now, and I thought I'd just share them. And if people have interesting questions, please ask me questions anyway along the way or chat. I think we have more than enough time. I'll just stop when someone tells me I'm out of time. So my research vision, you have to have a vision. You have to have like structure for all your grants and stuff. So my tagline I always use is to automate human decision-making in complex domains and environments in a dependent, dependable, and transparent way, which can mean a lot of things. My focus, I often kind of build out of kind of application domains or tasks or things like that. I like to find inspiration for kind of new algorithms. So I've been starting to like build it this way and say there's this cycle that go around for like finding new research problems or connecting them, is that, I can always talk about what, for every problem or project I'm working on, that what domain is I'm working on, what tasks I'm trying to solve, and what methods we're using to solve it, right? And sometimes, the domain is the place where it starts from, so that's how it was with the forest fire and forestry stuff when I was doing my PhD here. forestry department's next door, right? It's not the forestry preservation department, it's the how to cut forests down department, right? So if you ever go inside, obviously, right, it's all the wood. But it's all how to cut down efficiently and sustainably. So my PhD focused on, like, given the constraints they have for space and all these things, how do you sustainably manage forest? It's a very complex decision-making problem, right? So that's what I kind of worked on. Since then, I've kind of focused a bit more on forest fires, because it's kind of interesting dynamics, and obviously it's very apropos right now, so we'll talk a bit about that. We have some work on medical imaging, a lot with autonomous driving and human driving, so that's some project that we're just starting, is like understanding driving behavior. And the recent one, which we'll talk a bit more about at the bottom here, is these combining machine learning and AI with physics and chemistry and kind of like hard science data and models, and trying to use AI for that, right? So there's interesting stuff happening there. So these are domains of some Inspire work. The tasks we're trying to do are the standard, AI and machine learning tasks that we have. Maximizing, like basically planning, coming up with good decisions. There's a fair bit of work with anomaly detection, which I'm not going to talk about, and there's always prediction and classification. And then the methods I can tend towards is like reinforcement learning is kind of my home kind of area, but everything's deep learning, so you have to use deep learning because it works, so you have to use it. And there's always exciting ways to find out how it can work in the new thing or not. But we've also a fair bit of stuff on ensemble methods and dimensionality reduction, kind of more theoretical stuff. But I won't talk about those in the talk, but if you want to talk about them, I have stuff I can say. I also have a kind of parallel sideline thing that I often get pulled into and involved in stuff with AI for good or sustainability because of the forestry stuff. So I've been involved in a bunch of different things. This UN thing where they're trying to do AI for good and try to really do interdisciplinary connections of how to find AI uses and ways of helping make the world better in, like, not just climate change, but all of the UN sustainability goals. So we have this yearly conference there. And 1/3 of the conference are CS AI people, but another third are like government and social scientists, and another third are, I guess, business or something else. Very diverse group, and it's not just like our research conference, it's a how do we save the world with all this tech conference, right? Very interesting things. There's also workshops at all the big conferences. I helped with the one last year at NERPS, which was fun. And then there's stuff with fire, specifically in Canada and the States, because forest fire is getting worse and worse, and the tools that they have are not necessarily solving, it might be solvable, but helping as much as they hope. So they're more and more reaching out, saying, can we use this AI stuff to help with it? So obviously I say yes, but we're trying to figure out how to do that. But there's lots of that stuff going on. So if you're interested in trying to do things with AI for good, it's growing, right? So you should look at it. Okay, so I'll drill into a couple kind of example projects essentially, and each of these essentially like is a paper or presentation from some conference and kind of stacked together. So like a month ago or so, I was in Germany for ECML. It's a nice sized conference, like 500, 600 people, and it's like machine learning, end to end. It's not just deep learning. They had all kinds of stuff that people doing, association rule mining and rule learning and deep learning, and like lots of stuff on trees and random forests. So it was really nice. The thing I was there for was a bit more of an applied thing, and I came out of the fact that I'm in an engineering faculty, talking to mechanical engineers, having lunch with a guy who kind of both start at the same time in our orientation. My grad students have their orientation session, right? Profs have an orientation session too, right? So we have like our orientation, we have like people who started being prof at the same time, complain about writing grants. Anyway, so we talked about stuff. He tried to explain his problem to me, and I'm like, I don't understand, right? But he does like combustion modeling, right? So if you're going to design an engine to be more efficient, right, and have better fuel efficiency, you have to be able to simulate what's going on inside it, right? Which is fire and explosion, so it's complicated, right? So they have ways of simplifying it down. Well, I guess it has challenges, right? So there's physics in there, there's different scales of physics. So to make it like numerically kind of possible that you could actually run a simulation, you have to simplify it down, right? So one way to simplify is ignore turbulence. Great, I'm happy ignoring turbulence. But they have this model they use that is simple enough to calculate kind of lookup tables, essentially. But then they use it in a way that lets them build simulations that can run in real time, and they can try out different engines or energy production, right? And the idea is they create a very simple version of the flame that's flat. You got fuel shooting at it, and oxygen, an oxidizer in the other way, creates a flat sheet of fire, and they can calculate all the parameters of this thing very exactly around it, right? So they pre-compute these things using, because they've got partial differential equations that fully explain what's supposed to happen here, right? And they know how it works. So it's the kind of thing where the model itself is known. You can calculate it directly, right? But solving the equations to get that number is very expensive, right? So in a simulator, you wouldn't be able to run those equations all the time. So what they do is very sensible. You create a lookup table of all the values you might need in some kind of granularity of a grid. And then whenever the simulator needs something of that distance from the flame, they look up the value, and that gives them the energy release. And they're like, okay, that's what we'll use for the simulator, right? It's an approximation, but if this thing's granular enough, then it's a pretty good approximation, and it's fast, right? So they've been using this for years, and so a very simple version of it is really this three-dimensional table where they talk about pressure, mixture fraction, which is like the oxygen versus fuel level, and progress variation, which is very hard to explain, but it's something about distance from the core hottest part. And they've tabled these, look these up. This gives you an energy level, and you look up the energy level, and you can build your simulator, right? So we're like, okay, problem is, they actually have, to really explain this, they have 9 variables they'd love to use out of their formulas, right? So they want a 9-dimensional table with the same level of granularity, and maybe even higher granularity to run it. It's like, they can't do that, right? Because of dimensionality, it's too big, right? Even 5 variables, they can't do it. Because it'd be like 4 gigs, this table, and they wouldn't be able to run it on a normal machine. So I'm like, have you tried neural networks, right? Because obviously it's a lookup table with inputs and outputs. And is that this slide? No. So more slide convincing you that it's a very large problem, but you're scientists, so you're fine with that, right? Heat loss, so these are some of the other things they want, right? Like heat loss from the walls, other thermodynamics, various things that are important to accurately, calculate this. What else do we have here? Yeah, they try to do clever stuff like interpolation between different points. They have Bezier curves and they optimize the parameters of those to try to fit it so they can get more out of it. Or they just do a higher dimensional one, use PCA to get a 3-dimensional table and use that. So they're always hacking because all they can get to run is this 3-dimensional, maybe 4-dimensional thing, right? So I'm like, why don't you use a network, right? With all the inputs, outputs, and you can produce the energy release. You've got supervised data. The supervised data is perfect in a sense. You can just train it, right? And then, and then the nice part of it is that it's always interpolating, right? Because they have to actually, when they get their table, if the value they need is in between 2 grid points, they have to interpolate between them, right? You make a choice. Neural network, you automatically interpolate it, so it seems kind of perfect, right? So like somebody tried that, and it didn't work very well, right? Because they set up a neural network and they trained it, and it was worse than the table, it was slower and everything. And like, when did they try it? It's like, 2009, it didn't work. Some things have happened, right, since 2009. And so we're like, let's try it again with a bigger model and designing it based on how much data you had. When you dig into some of the things that other people have tried too, they also did it with like, 4 or 5 hidden variables and only this much data. So there's all the reasons that people weren't using neural networks after the 90s because it just wasn't working for hard problems. But since then, people have figured out how to train them better. And there's been some other stuff trying to use autoencoders with like images of the fire. So there has been some work, but not a lot yet. So we did basically that, and that's why this paper is coming more of application. But for the first stage, we've got to take in those 3 values and the data they have and try to train it. And there's 2 different things you have to train. You have to train the output percentages, like how much of each portion of chemical there is, and then there's things like well, I don't have a graph for it, but instead of so it's like a classifier saying how much regression for predicting how much hydrogen is left and how much OH is left after the thing is burned. But you'd have another network then that predicts like the energy release and things like that. So we have a bunch of different networks we trained for those data, and we had kind of many different architectures and hidden layers, but more than just one hidden layer. And we got them to generate a few gigs of data and kind of trained it. And we didn't really worry so much about like, oh, is it going to work better with 4 layers or 5 layers? Because often people are finding these days that's not the critical part. It's like the width of them and the nonlinear functions you're using. So kind of focused on that. There were a couple along the way. There were actually some interesting things to solve. It was because since it's an applied problem, when we produced the result, they're like, well, that's not smooth enough. That's not how these things should look, right? So they'd like have kind of qualitative reasons for the data being not good, so we had to do regularizations to kind of stop it from kind of oscillating, because it should be a smooth temperature curve. So we had to add regularizers, classification errors. Yeah, so we used ensemble of methods. So basically we learned multiple networks in parallel and took the averages of the top few of them rather than train one network to do them all. Kind of standard thing to do if you're doing a lot of deep learning, but it was instructive for basically a master's student did this, and it was kind of useful for learning that, and it's useful for them in that domain because no one knows how to use it properly for their data, so it's kind of like one example case, and how can we kind of build it out to something more complex. Hard sample, so the thing is very nonlinear, so I guess it's easier to show here, right? So certain parts of the curve have a lot more movement, so we kind of did oversampling in the areas where there's more data points and more change, rather than just having uniform sampling of the data everywhere. But we didn't have more data, so we could resampling of it, right? And this has kind of become a thing that people are doing, where you're oversampling of hard examples, and it helps. You're definitely biasing it towards the data you have, but it helps you fill in some of the cracks. And then using leaky values so that we don't have this kind of like value helps because it cuts off the negative results. You're only moving the gradients up rather than up and down all the time like sigmoid did. But if you make it 0, it actually causes certain problems. So we used existing models that say the nonlinear function should be basically not 0 in the lower part. And then we did a bunch of ablation studies where we talk about turning one or more of these model adjustments on or off and seeing which have contributed, right, more. And so the result of it was kind of that each of them kind of contributed something unique and different to making the accuracy better. And so the sum of the parts of it was greater than the individual parts. And so that worked pretty well. And the accuracy numbers here are a little odd, but they're definitely are comparable to using the table directly. And we're just kind of showing how it would improve if we turned one or more of these regulars as well. The most exciting part is more like looking at, okay, we take the simulation and then like replace those predictions from our model into the simulator of the fire and carry it forward. It still looks like the similar flame, right? So it seems qualitatively similar. But like I said, we've only done this so far on the 3-dimensional thing. This was looking at ECML. So now the student, and we're getting more data to do it on like 5-dimensional or more, because the fun thing about the neural network is adding more dimensions to the input isn't really going to make it much harder, right? We're still training on that much data. The network's learning a non-linear mapping. So it doesn't get bigger just because you add more inputs, right? This is the thing they kind of didn't really believe. So we have to kind of prove that, and then hopefully it's going to be useful in their domain, right? It's also a kind of useful example case. I'm going to use this in my machine learning course, my grad course next year, as like a way to do all the different like studies and experiments together. It's like, okay, here's to validate what you're doing. Just kind of, that was cool. Yeah, so that was kind of one interesting kind of side project that came up, and it connects to this more general theme of physics and chemistry within like using machine learning. Hopefully the next one is that. Yeah, I have slides on this winter road monitoring thing, but I'm not going to start with them. That one's fun too. But yeah, the next one is this thing is with, it's also with kind of chemistry like combustion, but it's more about like the job of a chemist who makes things and turns one chemical into another, right? So the NRC has this kind of new program that they're kind of pushing, and we've got some access to it where they're trying to like target certain areas like health and secure networks. I don't know how these connect at all. They're not connected at all. But it connects because they've got a lot of physicists and like hard science, like National Research Council, NRC, in Ottawa. So this is like the federal scientists, right? There's a job you could get. You can't get a university a researcher job, you get a job for the government doing research, right? They tend to do a lot of hardcore science, right? So like particle physics, other types of physics, chemistry, networks. They want to make faster, you know, fiber optics so that Canada can have better communication, right? So the government funds certain research. Materials is important, right? For the oil industry, but other things like pharmaceuticals and stuff. You're always turning one chemical to another. That's a big industry, right? So we got it for this thing, and I know somebody at NRC who does, he's a physicist who likes reinforcement learning, and he's been like basically trying to do, you know, make more efficient ways to do chemistry, and then he started reading about reinforcement learning, and we started talking, and like, oh, this is a perfect problem. So I'm gonna try to explain why it's a perfect problem. So as you know, I'm David's student, because when I talked about NDP, I show an influence diagram rather than like the math formulas or something. But I do it the other way sometimes too, but this is a recent form of it. So if you don't know reinforcement learning, or markup decision processes. I'll describe it, but I'll also use that problem to kind of fill in the blanks, right? So it's an iterative decision-making problem, right? So we have a state of the world, which tells everything that we know about the state that the agent is going to need to make decisions, right? Okay, state of the world, right? And then, so in this chemistry problem, that is, how much of each chemical do you have? How much phosphorus do you have? How much water do you have in, what are we calling them? Vessels at the beginning, right? And the pressures and temperatures of all things, right? So the state of everything that you need to know. Right? And then the task is that you need to take actions. And your battery dies. Oh, I turned it off. That's neat. Okay. Accidentally turned it off. And I'm going to give up. That didn't work. It could literally have died. Okay. No, it's too far. All right, how's it turn forward? No, it's okay. No, it's just the cables of the walls will be so long. Right. So the actions you're going to be taking, yeah, it's okay. So it's basically the idea is you got a chemical lab with a bunch of different benches that you can mix and match things and do different things, right? So you're going to add two chemicals together, you're going to mix them, you're going to boil one off and distill it. They have this process where they can extract contaminants in something by putting oil and water, and the ionization, one material moves out of the water to the oil, right? So these various types of things they can do, right? They're tasks, they're like black boxes, where you put a bunch of inputs, which are chemical mixtures, and you know how to get a certain output with some probability, right? Because usually they're not like certain what you'll get out, but you know how it generally works. And it has a bunch of, every one of these black boxes has a couple knobs. That's how I think of it. It's a physical bench, though. And then you get to measure something about the output. So how much is it of the chemical you got out, right? The rewards, which we talk about, we have states, we have actions, and then for a reinforcement learning problem, we have rewards. So let's say, once you do something, you find out whether it was good or not. You have to evaluate whether it was the right action, right? And in this domain, it's going to be like, well, did you produce the amount of the material you were looking for, right? How much did you get? How long did it take you? How much did it cost, right? Because the materials have costs, the time it takes has costs. So those all map pretty well. And then there's the dynamics of the system, which is like a transition function in an MDP. So you say, given some state of the world and some action, you have an output state, right? That's usually described as some probability function. And this is very well understood because chemistry is chemistry, right? So they have formulas that tell you exactly what an output of a very low-level reaction would be. But it's a similar problem to other areas where we know how the individual kind of actions happen, but we can't work out computing the end-to-end reaction across multiple things is very expensive, right? And you're searching that space, right? So there's well-known dynamics, but the policy we have to take here is to say, how do you get from a bunch of input chemicals through many different actions on these benches and black boxes to getting at its output chemical, right? So knowing the kind of low-level dynamics doesn't help you solve the real problem. So one thing I kind of started thinking about recently is if you describe problems this way, we talk a lot of different things in AI about if you have this description of states and actions and rewards, you can figure out what type of problem you're working on based on what parts of the diagram you do or don't know, right? So if you, and which ones you actually need to know, right? So a lot of supervised learning problems, you're essentially given states and next states, you're trying to predict the dynamics. You don't have actions, there's no rewards. You can kind of describe them a lot that way. But a decision-making problem where there's uncertainty and feedback and loops is kind of like full AI, where you have to, a lot of these things are present. And you have to predict them. So in this field, we know the dynamics, like I said, which is a bit weird, but we don't know the dynamics of the entire system because it's too expensive to compute. And we don't know the costs until we kind of try them. What we don't know is how to get through the entire kind of network to the end, because it's kind of a combinatorial number of choices we're going to take. What else is it? Yeah, and it's partially observable. So we also talk about that if you don't know what state you're in exactly, that is partially observable. And in this chemistry thing, you have a vessel that has some chemical goo in it, and you think you know roughly how much hydrogen, oxygen, and potassium is left in it, but you don't know exactly what happened in the reaction, right? And you can observe it fully by taking a bit of it out, destroying it in a spectrometer, and then finding out the exact makeup, but now you've actually used up some of your material. So there's observations like looking at it, which are partially kind of informative, but fully informative actions are often destructive, which is kind of an interesting twist, right? There's these high costs for finding out more information. That's why we're kind of interested in this problem, is that there's multiple different types of observations you can take, and they have different costs, which you don't see in a lot of other domains. So when I'm talking to physicists about this, when I was presenting it at NRC, I'm like, what is physics of reinforcement learning? Because we have the formulas that describe how we would estimate these different elements, which I won't go into. If you know it, great. But essentially all those different components in the graph, there's mathematical relationship between how they relate to the value of being in a certain state and following some actions, right? And which formula you use and which parts you know or don't know determines what algorithm you're going to take, right? We've been looking at policy gradient methods because we're kind of assuming we don't have all the elements, but I think we're actually going to switch to more of a model-based thing because we know a lot about chemistry, and so we should use that information as much as we can. But it's still it's a new field because no one's kind of doing this where we're trying to automate this entire process. So this it's not clear the right way to do it. So what we're actually focusing on initially is related to a lot of the way reinforcement learning research happens, is that it's based on these games and simulators. Like currently a lot of RL research is using video games. They're kind of going past Atari now, but you have a simulation essentially of the world. You can run it for many thousands or millions of episodes and train your policies, right? So for the science, this chemistry thing, we don't have that. So we're building kind of benches, simulated benches to let us simulate these processes and train them. They're necessarily have to be approximations, but the idea is that we want to make benches that represent, like simulators that represent all these different components, like a bench in a lab, and then have them released to the community and try to get people machine learning, working on this larger problem, and then make more progress. Of course, after we've got some results of our own progress. So there's reaction rate between two chemicals is one of them. You have things like you talk about, like vaporizing and distilling chemicals to extract different things. So you have like a simulation of just how that works, and you can optimize that. And then this extraction method where you put, you have some material that's contaminated and you extract it out by oil or something like that. So each of these on their own is quite simple in a way, and there's like one or two formulas that explains how it works. But having it available as like a simulator where they all connect the same way in reinforcement learning, this thing called Opening Eye Gym that a lot of people use, and they have these games and modules people can use. So we're trying to make one for science or chemistry. And then the idea is you're trying to simulate the real policy you want is how to be this chemist that can do things over multiple benches by choosing first, I guess, which environment to use, which bench, and then optimizing your policy within that at different layers of granularity, right? Yeah, and like I said, some of the interesting parts is that there's two levels of choices, kind of hierarchical, that you have to choose which bench to do at each moment, and you have to choose what you're going to do there. But there's also kind of very complex observations, right? Some of them are passive, some of them are destructive, and how do you trade off that? So this work's still in the early phases. We're building these simulators, but it's kind of an interesting question we're looking at is how do we choose trade off observations that have real costs on the goal that move you essentially backwards just to get information, right? Yeah, so that's another area. The next one then, I guess, is the fire. Does that work in here? Yeah, forest fire. So still on the reinforcement learning. So like I said, I started doing stuff with forest harvesting management with these spatial policies, and since then kind of gravitated more to forest fires because it's kind of a lot of interesting data there, but also a lot of need. So forest fire is forests are on fire and it spreads. People in BC don't need to be explained this too. When I present this in California, I made up this slide once and it was like trying to make sure everybody knows BC's bigger than California. And so there's actually more area burned here than in California in most of those years when it's in the news. But of course, there's a lot more people down there. So when they have a fire, actually, people die often. And so, I mean, I update this slide, unfortunately, every time I do a talk because it's something more horrible happened than the previous time I had it. So there's a fire on right now around Los Angeles. That's like 120 square miles, and it's not even fully contained yet. I don't think there's been deaths yet. But last year there was a really horrible one, and like 86 people died because they couldn't get out of the town fast enough, and it kind of moved so fast that they couldn't escape. So it's the kind of thing that you know it's coming. It's like there's a lot of preparation around it. Forest fire has got a lot of people working on it and researching it, but you still can't stop it, right? Because it's like in contrast to what some presidents say, you can't just sweep the forest and fix it, and it's not easy to solve, right? Because if fire is a natural thing, it's definitely going to happen in the forest. It actually needs to happen. Part of the reason it's happening so much in recent years, and it is happening more than it used to, they've studied that. A lot of it's climate change, right? It's drier, the winds are stronger and less predictable, the domain is changing from whatever that region was used to, so it's burning more. But some of it is also previous policies, right? So they used to put out all fires in the forests and kind of stop them because they wanted to get as much wood as possible. And so there's been a lot of buildup of old wood and dry things, right? So the policy you take over time will affect how likely it is things will burn in the future, right? And so that's a problem. So in terms of, from a computational point of view, it's interesting because there's a lot of data, the satellite data, there's entire ministries that collect information about this. It's very well understood in that way. There's simulations that people spend a lot of time building in forestry for how fire spreads and trees grow and all these things. They're usually very slow to use because the way they use it is manually, like an analyst uses it and then changes some of the parameters, but loads in their map, does a prediction, does a few different predictions based on their experience and intuition, and then writes reports based on those simulators, right? So when I was in Oregon, one of the things we were trying to do was take the U.S. Forest Fire Service simulator, the one they use nationally, and we rig it so that we could use it for machine learning. So we run it hundreds of thousands of times, but it would take an hour for a single, like you'd be running it forward at us, like you basically always have to run forward at the time, right? So to run 100 years into the future of one fire could take anywhere from like 10 minutes to an hour. If there's a lot of fires, it could take an hour. So you want, 10,000 runs for your machine learning, it's going to take a long time, right? So there's problems that way. They're not rigged up for the type of stuff we do. So I guess the kind of increasing complexity of things that I've worked on in that is like fire suppression. So what's the trade-off of like letting fires burn and do the treatment on their own, essentially? Because when a fire burns, it doesn't burn again for several years. So if it's not going to hurt anyone, it's often a good thing to let it burn. So you can analyze the impact of the action of not stopping a fire, right? Because you get a bunch of clearing for free, right? And we were able to show that that's often, like economically makes a big difference, that it's actually better to let it burn. But then you have to know in which situation, right? Because if it's burning down a town, then it wasn't worth it. And then we had the thing we talked about sustainable harvest. The thing that I'll present a bit next now is I'm trying to learn forest fire dynamics from satellite images, actually using reinforcement learning. And then fuel treatment is kind of the next thing. We'll talk about that a bit after. So this was kind of an interesting one. Last couple of years I had a student whose name will be on all the papers you see next, Serum, and he came up with, well, both came up with this idea of applying reinforcement learning to essentially learn agent-based models of how fires spread straight from satellite images. And it was fairly effective, and we're kind of trying to grow it with better data now. But the idea is they have models of how fire spreads, but climate changes, the situations are altering all the time. Not every country has entire forest fire ministries to build these models, right? So one way we're looking at it is, well, if we have satellite images which show kind of smoke from fires, and these are thermal images, so the hot spots are actually where there's some burning happening, so you know exactly where the fire is, and you have other indications in the color images that it's spreading. What we did, we were trying to say, well, we're going to treat it as if there's an agent on the landscape, agent is fire, and it's at every location. If it's on fire there, it has to decide where to walk and move next, right? So you could model fire that way. A lot of people in forestry do. They build, cellular automata. So the game of life, right? That cool little video game thing with all the circles, right? So you can build more complex versions of that, and it's called cellular automata. And a lot of people in like geographic information systems and environmental stuff, they'll build cellular automata using the rules they know about ecology or forest fires or something, and build a simulation and talk about the different outcomes that can happen. They don't learn it from data, they build it from knowledge and then look at the results, right? It's kind of the reverse of machine learning, but this is what we're trying to do essentially the other way around, right? Saying, like, if you get the data for something like this and you know how it's spreading, you could say, well, we're going to learn this agent, and we use reinforcement learning to learn that agent. Basically, if it didn't match the way the fire went in reality, it would get penalized. So it's trying to learn a general function for a local spreading policy that's matched to the satellite images. So we kind of built up a different kind of models of this. So we started just trying to use the deep cube learning kind of methods that are popular recently, because they take images out, they give you actions out, take images in, actions out, and it works all right. We kind of built in and things essentially reconstructed the same kind of thing that DeepMind finds with AlphaGo, which is not surprising because they found an algorithm that works well for that, which is to say that a combination of local tree search, those that are running forward of tree search, of trying out different actions and seeing their outcomes to help you evaluate possible choices, and learning from images and trying out different actions. A combination of those is very effective. And so it's kind of the same thing we were finding. So because it's for the fire, you can see it essentially it's a bit kludgy because the step it's taking in the action space for the reinforcement learning is kind of very immediate, but the next image might not be for until the next day or a couple days later, right? So you have to take many steps until you get to the actual size, right? So there's another parameter to figure well, how many steps are we talking before we match the image? And essentially, you want to see if it ever matches the next step. And then we had this kind of comparative study again to talk about how to do your experiments with other methods. Like Gaussian processes take something that's much more like supervised learning. You just say, well, here's the data, the input and the output. Can I learn a spatial model of that, right? And in this image, I'll just look it up. Oh, I don't have my key. Red and black are good. White and blue are bad. Because red means we predict fire correctly. Black meant we predict no fire correctly. The true positives and true negatives. White and blue are the other ones, so we predicted something wrong. And the ones that work best are these ones that use tree search and these kind of latest deep RL methods in combination. Whereas the supervised method, at least on our data, didn't work quite as well. But there's ways to improve it. One thing we're trying to do with these is to get higher resolution images and kind of more frequent images, so every day or something, so that we have a better chance of kind of predicting that dynamics.
Just a quick question.
Yeah.
Can you describe what the action space is there? Like, so it makes sense to me if you're trying to fit some kind of a PDE to your data, but,
yeah.
But that's not what you're doing.
No, yeah, the action is that at every location, if there's a fire, at the next time step, does the fire spread to one of the surrounding cells or pixels, right? So you're learning a policy that applies at every location, essentially based on its local environment, right? If there's no fire there, then there's nothing for it to do, but if there is fire, which way would it move, right? And you might have the images over time that you're trying to figure out where it's going to spread to next. So it's, this image on the left is kind of the closest visual thing I have of the policy. But it's using, it's not drawing the perimeter explicitly. Every pixel has the policy being used about, given the conditions around it, which way it would spread. And so the next step for these things is kind of similar that we're to what I talked about with the chemistry lab, is that we're trying to build a simulator that people could use. Because like I said, the simulators that kind of exist for forestry and forest fire are not very accessible, or they're like toy things and they're very simple. So there's no middle ground one like the OpenAI Gym that's useful and modular and everybody can use. So we're building one that's kind of like base level that has all the features in it that you need, because we've spent a lot of time talking to forestry researchers, I have over the years, so I kind of know what they need, and I can ask them, like, is this reasonable? So we're going to build a modular simulator. I've been hiring undergrads for a couple terms, helping PhD students do this. And essentially, once it's done, we'll kind of release it as a new kind of game where you could have a domain, you load it in as a real map, and then you try to affect or stop the fire or affect its course in this year or future years. But the idea being that once it's accessible, you could plug in different modules to make the fire or the forest like ecology more accurate, right? Because there's always going to be some level of approximation, but the ones that they use in their field are like too detailed, right? And then other ones, people make ones that are twice, like too simple. So we want something that could ramp up and actually be realistic. But this domain has interesting things as either you just think of it as a video game. Like it's not, like video games are good for reinforcement learning, but they only go so far, right? Because the video games that people find fun aren't necessarily the ones that are going to help us solve real world problems, right? So like, you know, Pong and all these kind of Space Invaders ones are really easy for the computer to beat, and Montezuma's Revenge, which is one of the ones essentially where you have to get a key and go save the princess, whatever. They're very hard, but is that related to like a real world problem, right? There's a real world problem. It's got some other dynamics. It might not be the most fun game for humans, but we can treat it like a game and see if the AI can learn it. Because if it can learn it, then it'd be useful for planners to decide what to do, right? Because they could input their maps and their models and help them augment their decision making, right? Because they can run forward in different scenarios. Because they got to do something that the way they're planning now is not necessarily helping, so they have to kind of find some way to improve upon it. Yeah, and so one of the parts of this that's interesting is like you can get a very small change in the output, and one fire is not so bad, and another fire is catastrophic. That somehow becomes a much larger spread. So can you even, as a simple problem for these domains, could you predict whether this fire is going to be catastrophic or just normal bad, right? How do you predict the difference? And it seems like this kind of non-linear black swan type thing, but if you have models that are kind of realistic, maybe we can help predict that. And you know, that won't stop these fires from happening, but it'd be never we could evacuate earlier if you could predict it. So that's kind of a concrete one. And like I said, if you have questions along the way, feel free to ask. I'll pause for coffee and go back to my pen.
So is it spatially invariant, your model? So you have a different model for each point in space? If so,
no, it's the same, yeah.
But does it depend on, do you have other information like ground cover, elevation, slope, weather conditions?
Right, yeah, you should. So when we were doing that, we were just using straight images on those photos, and this was our ground truth, is the heat maps. But it's invariant, so we're using the same policy at every location. But if you're doing it, like the next stage, we would have other maps in like elevation, weather, like you're saying, other things. Some of them are hard because they're different levels of granularity, right? So the wind and weather are very high regional things, and then the fuel level and elevation is very detailed. So you know, the wind, they just tell you the wind for the entire region of the province. But does it apply at this location or not? You could get it. Yeah, we weren't using it here, but you could get that. So that'd be another level. Yeah. If I get a student to work on that. The student who's been doing this is now working on that simulator thing for the multi-agent problem. So he's now working on this. I think he was next. Yeah.
So my domain is computer vision. I'll talk about examples from that, but it connects to this.
Yeah.
So one of the problems with you having computer vision right now is that when we train a neural network, we don't really know what happens if we give it a random image or something that the network hasn't seen before. And the problem comes from the fact that we don't understand the generalization properties of this model. And basically, wherever we have a deep network, that problem also comes with it. And especially the first part of the problem and later in the reinforcement learning part, we know some of the important shortcomings that we have with deep networks. For instance, the reinforcement learning, the Atari game that you showed, we know that if we change the texture of the game, the strategy is not going to work anymore because the system is not able to extrapolate beyond the samples that it has seen.
Yeah.
So in the first part of your talk, you talked about replacing well-understood models, dynamical models, with approximations of a neural network. So my question is, because you're essentially replacing an open box with a black box, that you don't really see what's inside. So my question is, how do you verify the correctness of your approximation? And how can you guarantee that it will behave the way that it's supposed to when it encounters something that it hasn't seen before? It becomes more relevant in the later part of your talk when you want to model the spread of fire, for instance.
Yeah, yeah. No, you definitely can't. You can't guarantee it. If you're using deep network to model something, you can't guarantee what it's learning and what its output's going to be. So you might be able to interpret it depending how you structure things, and you might want to build in kind of more rules, constraints that let you do that. But you do have to give up on guarantees because you're learning something that's soft and is moving towards an optimal. But I don't think that's something you can really build into it. So, but there's these trade-offs of what's going to be useful, right? So for the combustion one, they're already using approximations that's acceptable level to them of accuracy, and it helps them speed it up and do their experiments, right? So for that one, we're just going to try to recreate the accuracy levels they're comfortable with already. But now if you say, well, we can handle 3 more dimensions that you couldn't with the same level of accuracy and the interpolation's even better, that's still okay, right? Because that's what they're used to, right? For fire, it is a problem, right? Because this is going to end up being real strategy, like a policy for public policy. And so can you guarantee that this fire is not going to burn down this town? And be like, no, right?
It's not just that, even in the combustion model, which appears to be simple. So the table, the information is calculated from ODEs and like models that you have. So there you can bound the error. With, like you have a precision measure, you have a measure of precision, and you can bound the error. And the table that you have, you would know the information that you're using is reliable to some extent. But I think it becomes even more problematic when you go to a higher dimension prediction, when the input has tens of, like let's say even 10, not going even beyond that. And you're making a regression type problem, you're making numerical predictions. For instance, the thing with deep learning is that you can show that it's not smooth function. Usually the function that a neural network learns is not smooth. So if you perturb the input image by epsilon, the output is not bounded, or the bound is really large. So like in an OD setting, we typically have this continuity and a measure of how fast things can change. Whereas in an approximation linearly, we don't even have that. So wouldn't that be like, wouldn't you need to have some sort of verification that this model that I'm using is correct? Because let's say some part of the simulation, it runs into a region of the space where it's not reliable. What's going to happen then?
Yeah, so I mean, at this point, the methods are all empirical, where you say, well, we're going to try and explore it fully in that area and do the bounds of things that are reasonable, and say, does it empirically? We've never seen that. What's the probability based on the experiments, right? But you're right. It would be better to build something that you could have that. I don't know of one right now, but for the smoothness, that was the thing where we had a certain level of smoothness we wanted to achieve for that thing, and then we kind of empirically evaluate it and add regularization until we can get to that. But at some level, that could always happen, right? But in their model, in their original approach, when they don't have something on exactly the point they calculated for, they're doing like linear interpolation between those points, right? So they don't have that risk of being outside, but they're probably not following the true function either, right? It's smooth, but it's not accurate. So
but at least in linear interpolation for
it's
points that you don't have, but for deep learning, you don't even know what happens to a region.
Yeah, so it's a thing you can't get away from. I'm all for like interpretable models and building it in there, but this is the way we're trying right now. Did you have still a question?
Yeah, just a very quick question. I'm intrigued by your choice of reinforcement learning to solve this problem. There are many other ways actually to solve it. So what's the advantage of using
hopefully there is an advantage, but that one was useful. We're trying to scale it up to higher data and see if it's still an advantage. It was an interesting kind of idea to try out. So the student was like, let's try this, reinforcement learning. And then it became like this idea of learning an agent-based model I thought was kind of interesting, right? Because many people in those fields use agent-based models. We're trying to learn a model of the rules locally. And then the hope is that it might be more interpretable, right? We have a policy that says, here's how fire spreads locally, right? In terms of accuracy, we didn't compare it, so we compared it to Gaussian processes because it feels like, well, that's supervised, they should be able to learn it directly. And for that domain, at least, it wasn't better.
I come with a control.
Okay.
And we found that reinforcement learning is not sample efficient.
No.
No,
reinforcement learning is not sample efficient. Would be a good T-shirt. No, but I mean that's not what it's necessarily trying to do. Me and Michael were talking about this earlier. It's like the difference between control and reinforcement learning, and they're trying to do the same thing, right, from different approaches. And control's focused, I guess, more on the guarantees and then what you know, and reinforcement learning trying to basic, how do we learn if there's certain fundamental things like the dynamics, we don't know them. How would you do that, right? And then you give up sample efficiency, you give up guarantees, but the goal is, can you learn the way a child or animal can learn, right? So it's an AI-directed approach, but it seems to be useful in certain domains anyway. So how do they connect? Where do they meet? I think that's an important discussion to have. There was another question there.
It was just on the combustion experiment.
Yeah.
You may have said it, but I missed it. What was the error metric, and how did the neural network do in the end compared to the tabular approximation?
Yeah, it was. I don't have it here exactly right now, but it was a thing where, like, on the actual data points, it had, you know, a certain error level, because the table we're comparing against essentially the table, right? The table is computed exactly for those points.
Or you were comparing against the ground truth, the model.
Well, the table is the ground truth for those points. So we did like leave out training, right, where we didn't train on all of the points, and we tried to interpolate points that we weren't given in training. But the values that are in the table are as true as you can get in that domain, right? But then I guess the value, so obviously had an error, so it was worse than the table on the actual points, but better in between them, right? Because interpolation, it was doing more of a nonlinear interpolation between the points, but their approach is essentially to take, if you wanted the value between 2 points, you do linear interpolation between them, right? So, but that's kind of arbitrary, that's just what they use. So the real test is going to be more when we get it in and plug it into an actual simulator and say, now we've learned this model of a neural network for that instance, and replace the table, and then run an entire simulation of some other experiment of like an engine, and then calculate the performance difference on those things. But we haven't done that yet. Yeah, but it seems like it's all potential, but it's kind of, this is the first proof of concept of it. Yeah.
So you mentioned that you're very much interested into this interpretable, transparent models. I think so far you haven't.
No, yeah, I'm interested in it. I don't have any big examples of it yet, but it's so much. So I said that, I think we should.
Because these are all critical applications where probably having that kind of transparency and interpretability is probably useful for.
Yeah.
Especially the end users, right?
That's right. Yeah. Trying to think if there's anywhere yet, because we kind of get focused on, you know, that domain and getting an initial result for it, but you know, trying to build some kind of like logical or graphical model that represents the interactions between the variables directly, and learning that, or extracting that from the neural network would be something that I've thought about doing. But at the moment we don't have anything.
Because a lot of people have been working on trying to, you know, come up with methods to make, you know, especially deep learning models more interpretable. But I haven't seen a lot of evidence that, you know, especially for end users, they would work.
Yeah, and there's ones with all, like, when they do it for like image classification, that they show you what the network is thinking about at each layer. It's like, okay, that's kind of qualitatively interesting that it sees beaks and eyes or whatever, but how does it help the user, right? But it's critical for the fire thing, because when you talk to people and you found this at the workshop, right? When the people from forestry see it, they don't want a black box. They want something that they can tell why it's making this decision, because they have to, the person's going to actually make the decision, and they're responsible for the results, right? So that was kind of the motivation for trying to learn these things, where you learn the reinforcement learning policy from the images, because then you're at least saying, well, I can explain now, even though it's going to be a probability output, I can explain it as like, if you're in this location and it's on fire, here's the probability going north, east, west, south, given the input values. So we could create a kind of explanation. That was kind of one of the motivations. For the next stage of planning, we don't have an answer for it yet. It's hard. Okay. I'll skip something then. What was the next thing? What did I have after that? Yeah, so this one's too long to talk about in 5 minutes. So I'll give you the main idea. So we also have a couple students working on multi-agent reinforcement learning, and they're actually both kind of graduating students. So I'm not sure what the next one's going to be for this. But this problem, we had this at RLDM and AMAS this year. And actually, Nando's on one of the papers that we're like extending from, so it's connecting them here. But the idea is you've got multiple agents in a domain, so it could be, in our case, it was like controlling multiple cars, and you want to control the multiple cars or agents so that they don't crash into each other and do, you know, operate well, but they also have the ability to communicate to help reduce kind of the non-linearity of the system. So when you have multiple agents, the problem with reinforcement learning is that it's non-stationary, right? So you could find a solution, but then another agent could do something different, and it will move away, right? It's kind of the problems they have in game theory, but we don't have any kind of guarantees here. So if you communicate with each other and kind of collaborate a little bit, you can get rid of some of that and still find an optimal policy. So there's kind of a literature already with these IMS and DIAL or other papers that do that, and they try to learn, but using deep learning, so we're learning an uninterpretable neural network for the policy, but where we also learn the communication channel between the agents, so that they can figure out how to coordinate and say, well, I'm going to move right, so you move left, right? You don't tell them what that language has to be. You just add that in as more parameters, and you train it with backprop, right? So they're learning a language to talk amongst themselves so that they can solve the problem better. It's a bit pretty deep, but it kind of seems to work to stabilize the problem. And so we had kind of an additional thing on this where, what did we do different? We had a new architecture where rather than some of the previous methods had like multiple agents interacting, so every agent had their own network, and they would like aggregate all of the messages from the other agents and use that as some kind of input, and then they could all operate based on this aggregate message from everyone, right? And so the student was working on this was saying, well, let's use the actual messages from every agent, but do it in kind of in sequence. So once agent 1 takes its action, it would send some message, and then all the other agents could respond to that in that same time step. And then when agent 2 takes it, its messages get sent out. Whereas the previous methods, it kind of aggregated it from previous time steps, something like that. And so we kind of had two different approaches where we did this locally, and it was more stable and improved on the results for it. The other aspect of this is that if you're talking about cars and they're communicating with each other, they might lose their signal and not always be able to respond to each other. So you want to learn a communication strategy where you use the communication to stabilize the learning, but then you could try to say, well, now let's try to learn a policy where we don't need the communication at all. And so we kind of created a broadcast kind of scenario where we send the message out and broadcast back to everyone, and then if you train it so that you don't need the message at all, and it seemed to work. So I guess we had some plots, shared plots, where the two other methods we were comparing to. This is on our own domain. We had another domain with the plots here, where we had kind of cars driving on a highway, and you had aggressive cars trying to crash. And I guess it was the reward that we're gaining over time. That red one is the one I was talking about, where each of them is taking the message kind of as they go, rather than from the past steps. And it learned kind of good policies faster than the previous methods, which was encouraging. So we're going to try to expand it onto other domains soon. So yeah, it's kind of like just a sample actually of the reinforcement learning kind of areas of some of my work related to these physical systems. We've got a whole group of students. Like I said, some of them have graduated, but there's other ones coming in, and there's other topics, but those kind of summary of some of the stuff going on. So if there's any questions, I'd be happy to talk about it.
In the combustion modeling example, you mentioned the idea of oversampling and undersampling, can you elaborate more on that and what is the criteria and what determines when you do the oversampling, and do you have any thoughts on how to apply that to reinforcement learning?
How to apply that to reinforcement learning? What was I don't remember what the criteria was exactly. I can send you the paper and you can look at it. It was essentially the high curvature areas of the energy function. So we have a function where we have a definition of like hardness, right? So it's kind of arbitrary. You put in something, but you could figure out based on how quickly the values are changing. And say that that area, that region of the inputs had to be kind of oversampled. For reinforcement learning, I guess you could use the same idea. The idea is like areas that seem to be harder because you're not kind of converging quick enough. You want to get more samples. There's this notion in reinforcement learning of optimistic search, right? So if you haven't tried something, right? So I don't know if this applies. I'm just thinking on the spot here. Like if there's an area you don't know anything about because you've never seen it much, you should go. If you have a choice of which action to take, and one of them from this state you've basically never seen it or you have low confidence about it, you should take that action because it's something you don't know. So either you'll be wrong and you'll learn that quickly, or you'll be right and it won't change much, right? I guess this oversampling of hard problems would be more like, well, right now, I guess, in reinforcement learning, they do a lot now more of experience replay, right? So you run a bunch of trajectories with your policy, and then you do replays from your history, and you look up some previous state action pairs, and you train on them again, right? And so I think people do that already then, which is basically when you're choosing from your experience replay buffer which states to sample, you should get the ones where the reward seems to be low or the uncertainty is low for somehow you'd have to evaluate that. But yeah, you can do that in the way you sample the replay buffer.
Yeah, I'm in game development, and this is interesting to me as potentially a way to optimize complex physical simulations.
Right.
So we do a bunch of stuff with plot dynamics or destructible terrain or buildings falling over. There's a bunch of places where we're calculating a result in some way, and we wish we could calculate it faster.
Oh, right.
And we don't really care about transparent models as long as it looks good and runs quickly and runs great. Do you think, I recently became aware of work at Miguel and Ubisoft in Montreal, where they were using machine learning to simulate clock dynamics. So they would animate a character, and then the clock dynamics was effectively learned. It's cool because you've got an existing engine that can simulate the correct answer, so you can easily generate lots of data to train up the neural network on. Hopefully the network is a lot cheaper to run than the physical simulation.
Yeah, that's the thing you can compare. Because the neural network, they're not free to run either because if they're really big, but there's just a linear forward run of all these weights. So it's faster than a lot of things. Like in R1, it's slower for sure. Like the lookup table is much faster. Right, because you can't even running a network forward. But if it's got this higher dimensionality thing, it'd be worth it. Right?
Another interesting thing about it is potentially it could be running the neural network might be more deterministic than running the physics simulation, because if your physics simulator is using a ton of floating point math and all kinds of functions and stuff, but your neural network is a very simple operation that you can implement in fixed point, you could use it in a peer-to-peer game where every client is running the same simulation with the same inputs and has to get the same results to keep the game in sync.
All right.
But now if you could apply that to building destruction, then the building can fall over and affect gameplay and not be just an aesthetic effect.
Right.
So there's a bunch of interesting potential applications.
Building destruction, simulating buildings fall over. But I mean, you could also train it, I think you could say, well, we're going to train this network with the constraint that it only has this range of answers, or like the outputs are only using this many bits, and so then it would have to learn, it'll optimize to whatever it's given in terms of what it's allowed to output. So you could say it has to be this small, and then it would be faster. And it would do the best it can within that, right? And it's usually, I think, people find better to do that while you're training rather than do it after the fact. So if you train it with like lots of freedom and really hot big variables, and then you say, no, let's just summarize it, it wouldn't necessarily be best. There's another prof at Waterloo in system design, Alex Wong, and he does stuff where they train the entire network fully connected on some problem. I think it's for medical devices. And then they interactively search for the arcs they can drop out. I think they actually use genetic algorithms for that. So they look at the networks after they've trained it. They then say, well, can we drop which arc? Can we drop some arc from the network? Essentially, delete it, and then run forward and see how good it is and evaluate them. And they search for when they can make it 10 times smaller, and the accuracy goes down by 0.5%. Because you don't need most of the arcs, but you don't know which ones you don't need when you're training. But after you've trained it, you can make it a lot smaller and faster. So that's another practical thing too. After you've trained it, try to optimize the network, but do it in a way that you evaluate how much you're losing, I guess. Yeah. Cool, thanks. Yep.
It seems like, at least for some of the applications, but specifically the forest fire, when you're doing strictly off-policy reinforcement learning, because I assume you're not able to
actually start for a fire and that. Yeah, I think forest fire, it's all going to be all policy, yeah. And the timeline is just not, you can't ever try this, right? Because you're going to try it and people will implement the policy and then they'll follow it with their own input, so they wouldn't even do exactly what your policy said. They would do something else. So it's a little hard to deploy for stuff. I have found this. But it means if we can do something which is a useful decision-making tool for people, it's an input to another bigger system of decision-making. But sorry, is that your question?
I guess if you're doing strictly off policy, do you think there's any way to like further improve like how it's implemented in practice by including some like uncertainty or something like that, or like I don't know. I guess is there a nice direction to go with strictly off policy reinforcement learning for like safety, basically? If that can make sense.
Right. Yeah, to like improve the confidence that it's giving you the right answers. Yes, I'm sure there is. Yeah, for that one, the things that we're just trying to do prediction there, it's the safety isn't about like the actions we're taking because we're not carrying it out yet. But the next stage, what we're doing is going to have actions, so we'll have to include that for sure. Yeah.
In many complex physics domains, you have models at different scales that usually have very different internal dynamics and structures, and it seems to be a notorious hardness in different fields to couple these multi-scale simulators.
Right.
Could you potentially do something like for neural networks that are learning to predict spatial important parameters, like a combustion network, to use that as a coupling between different layers of simulators? Because they would be kind of like learning aggregate important features, which are maybe relevant across scales.
Yeah. I mean, it's possible. Neural networks can learn anything you want them to learn if you give them the right data, right? But it's a question of how hard it is. And always be wary of something where physicists say this is notoriously hard, to not think it's easy because they usually have explored it in some deep way. Because if they're completely different models, like essentially at a lower level is doing things that are represented completely different than another one, it just might be better to learn the models of each of those layers and treat it hierarchically. That like, are we transitioning to the next one, rather than learning a single model for both? But that's just my gut.
I mean, learning something which helps in transitioning between.
Yeah, you specifically train one that says which level are we at. You switch from level 1 to level 2 in the hierarchy. You could do that as a classifier, right? That makes sense.
All right, thanks the speaker.
Okay.